All right, good afternoon, everybody. Let's get started. Welcome to 6004. Today is actually the last lecture of the course. And as you all know, we have a quiz review tonight. There's no worksheet associated with this lecture because the contents of this lecture either are not in the quiz, or at least not in the quiz directly. Instead, what we're going to do in this lecture is a couple of things. So basically, we're going to go back to looking at processor performance. And at a high level, we've seen two key techniques to improve performance. Pipelining, right, to improve the clock cycle time, or the clock cycle frequency. And then caches to reduce the impact of long accesses to large memories, right? So these two techniques were the basic techniques of processors built up until the mid-80s. And all other processors, processors that you can go buy today, use these techniques, but they also use several other techniques. And so what we're going to do today is on the one hand, we're going to look at this and just do a high-level overview of the key techniques that modern processors use to get higher performance than the simple pipelines with just simple caches that we've seen so far. Now, this is good because, first you'll see a connection of the techniques, how the techniques that we've seen are connected and can be expanded to, get to processors that are actually built today. And it will also make you, knowing about these techniques will make you a better programmer, because it's good to know what the processor is doing to help you run code fast, right? It will guide you to do good optimizations. But more importantly, we're going to emphasize a few techniques that may help you, that you may find very helpful in the design project. And so we'll look, for example, at what can you do, with the processor pipeline that you start with in the design project. Some optimizations that you can do, like increasing pipeline stages and doing simple branch prediction techniques to reduce the impact of taken branches. So essentially, what I want to do is use this as a vehicle for giving you tips to do well in the design project. All right, so this is a reminder. This is the iron law of processor performance. If you want to analyze the time, or you want to minimize the time that a program takes to run, you can express this as the product of these three fractions: the number of instructions per program, the number of cycles per instruction, and the amount of time per clock cycle, right? So the two things that are under our control, if we have a fixed instruction set, are the CPI and the clock cycle time. And what we saw is that pipelining is all about lowering the clock cycle time, right? Increasing clock cycle frequency by doing less work on a given clock cycle and spreading the execution of each instruction over multiple clock cycles. Now, in terms of CPI, right, this is the number of cycles per instruction that you take. And it's helpful to divide this into two components. What we call the ideal CPI, what happens, what's the best cycles per instruction that you can get if every cycle your processor is doing the maximum possible amount of work it's designed to do, right? So for example, in our simple pipelines, this would be executing or fetching, decoding, and executing one instruction every cycle, right? But as we saw, the problem that we have the moment that we start introducing pipelining, and also many other techniques that we'll see today, is that we have stalls, right? And you have stalls due to different kinds of hazards, what we call data hazards, right? Dependencies through registers, right? So an instruction may need a register value that is produced by a previous instruction. It might also need a memory value that comes from a cache miss, and so that instruction may be waiting for tens or hundreds of cycles for the data to become available, right? And then control hazards happen every time we have an instruction that needs to redirect the control flow of the program. Any instruction that sets the PC to do something that's not PC+4, right? Okay, so let's go back to the 5-stage pipeline, right? This is the 5-stage pipeline that we saw in lecture 20, and assume that there's full bypassing, right? So this has, instruction fetch, decode, execute, memory, write back, and then we have bypass paths here, here, and here, right? So at the output of execute, memory, and write back, and these are going to decode. Those are the 3 bypasses that we have. So the ideal CPI of this 5-stage pipeline is 1, right? If in the best possible case, we're going to be sending 1 instruction down the pipeline every cycle. Now, the problem is we have data hazards and control hazards. If you have full bypassing, remember that you don't have data hazards on operations, or you don't have stalls due to data hazards on any operation that is register to register, right? So the only thing that causes a stall is operations that load data from the data cache, right? Because we have the result of every operation as early as execute, and so we can bypass it to the instruction in decode. So even if you have 2 instructions next to each other that are consuming, the later instruction is consuming some value produced by the earlier instruction. If that's produced in execute, then we can use it immediately, right, by bypassing it. But we have a problem with values from the data cache, right? So can you tell me how many, if you have, let's just look at this particular example, right? So I'm showing a loop over here. So you have a load, a loop where each iteration is a load instruction, and then it's immediately followed by an add instruction that uses the value that the load instruction loads as a source operand, right? So you have a dependence here. So in this pipeline, how many cycles are you going to lose to stalls to wait for the result to be available if you have full bypassing? Yes? 2, precisely. Why? Because the result of the load is available only on write back, right? So that is going to introduce some inefficiencies, right? Some utilization issues. We're going to keep the pipeline idle for a couple of cycles. Great. So the other source of CPI hazard is control hazards here, right? And remember, here we're predicting, right? At instruction fetch, we don't know what the next PC is for sure. And we have some instructions, branches, and jumps that change the PC. But by default, what we're doing is predicting PC plus 4, right? We're always predicting PC plus 4. And if later on we find that we have a branch that's taken or a jump, we have an annul signal that essentially lets us know that we have mispredicted, we didn't want to fetch PC plus 4, and we need to annul what the earlier stages of the pipeline are working on and redirect execution to the right PC, right, to the target of the branch or jump. So can anyone tell me how many cycles do you lose to each jump or taken branch in this pipeline? This one is less obvious. So let's I've copied the code here just so that you can see it, and then what I will do is draw the pipeline diagram for this one. Okay, so we have fetch. Yep.
You're not showing the code if you meant to be.
Okay, which one is it? There we go. So we have fetch, decode, execute, memory, and write back. Right? When we are on the first, let's just do a few cycles right when the branch instruction is taken. Right? So we start with the branch here. This is fetching, the pipeline at this point is fetching this instruction because we predict PC plus 4. right? And then we have immediately for it we have add I, add, and in fact here we have an op because this add was waiting for the load. Okay, so this is, let's call this cycle 0, right? This is right when the branch is in the decode stage. Now, the branch has, this particular branch is reading A0, right, which add-I is producing, so we need to use this bypass. But if we have the execute bypass, we can let the BNE proceed to execute, right? So this is how the later part of the pipeline looks, right? Now what happens here? We move sub to decode and we start fetching XOR. Now what's going to happen in the following cycle? So in execute, we figure out that the branch is actually taken. This is branch if not equal, right? And assume that you're doing this loop, you're doing many, many iterations. So this branch is always taken, but we're predicting not taken. And so we need to annul, right? We need to redirect execution to the load instruction. So in the next cycle, the load will be in fetch, the XOR and the sub will become no-op, so will be annulled, and the BNE will be in memory, the memory stage. Okay, how many cycles have we lost here? For how many cycles are we not going to be committing or doing write back of an instruction? How many no-ops are there in this pipeline? Yes, 2. So you have 2 cycles, right? We're adding 2 cycles because we found 2 cycles later that we actually didn't use the right PC. Right? Okay, so 2. Okay, now let's look at a slightly different pipeline. So this is a pipeline that we suggest you implement in the design project, and it is not a 5-stage pipeline, it is a 4-stage pipeline. And it has 2 important differences. The first one is there's no memory state. The reason we do this is because this actually is fast enough that it doesn't affect the clock cycle too much, so you can merge memory and write back. So essentially we start driving or giving the load request to the data cache in execute, the load or store request, and then there's only a write back stage here. The other difference is in the fetch stage. So this fetch stage essentially recommend that you implement it this way, and the handout has much more detail into what is going on here. Part of the reason is that this will make your implementation easier, but the other good benefit of this versus the previous fetch stage is in the previous fetch stage you have the PC register here on top, and when you annul, right, when you have this prediction, you take the new PC, write it into the PC register, and then on the next cycle, start using it, right? And give it to the input of the instruction cache. This is not what's happening here. What's happening here is on the same cycle that we detect that there's a misprediction, right, in execute, let's say that you have a taken branch here, we are directly feeding the new PC to the instruction cache on the same cycle. So now, this is, we call PC bypassing, and if you do the pipeline diagram for this, it will be very clear why we call it PC bypassing. So, So we have the same situation as before. We have sub, BNE, add I, and add. And then BNE proceeds to execute. Sub proceeds here. Add I is now in write back. But we do something different. We start fetching at this point in this cycle. We figure out, oh, this is a taken branch. So we're going to start fetching from the next PC immediately. We're going to bypass this redirect PC to fetch, and we'll actually start fetching at load. So we, whereas here we fetch the XOR instruction, here we don't, right? So what happens on the next cycle? Well, load progresses. It's correct instruction. Sub, however, we need to annul. So sub becomes annul, and BNE makes it to write back. And then, of course, we're fetching from the next instruction, which is the add. Is this clear? We've started the fetch one cycle earlier, right? So how many cycles are we losing here to mispredictions? 1, which you'll see is great because the project asks you to optimize the processor for sorting or your quicksort implementation, and that has many branches. So making, going from two lost cycles to 1 actually makes quite a big difference. The other source of CPI hazard is Theta Hazard. So how many hazards do we have here due to load to use stalls? So from this load to add, since we have 4 pipeline stages instead of 5, remember before we lost 2 cycles because this add had to wait for 2 cycles for the load to be in write back. But now, how many are we going to lose? Now there's no memory stage, right? So instead of 2, we're also losing 1 because there's 1 less pipeline stage. Okay, and this is also 1. Any questions? Yes?
What do we do now that we don't have the memory stage?
Enjoy the lower stalls. I mean, there's the reason you can do this is because it doesn't impact clock cycle time. And so the shorter pipeline will just give you a better CPI. That's why we recommend that you do this by default. So, there's no reason to split things into that state. And there's actually, a good reason why these things are different, right? Why we're doing these optimizations. The reason is that in the standard 5-stage pipeline, the assumption is that both the instruction cache and the data cache have a lot of delay at the beginning. So when you give them an input, an address and a request, they're going to take a fair amount of combinational delay until they start processing it. But in the caches that you build and in the single cycle memories, this delay is actually very small. So that's why we can do these optimizations, both the PC bypassing and removing the memory stage. Okay, so even though you have lower stalls here, right, with 4 stages, you might actually see that at some point you might want to create a 5th stage. And we'll see that in a little bit. Okay, so these are simple pipelines, but what do modern processors do? Well, on the one hand, they have what we call deeper pipelines. So rather than 4 or 5 stages, they have around 20. Now, even if you have very long pipelines, you can increase the clock cycle time, but you can also do more work per cycle. And so instead of executing a single instruction per cycle on each stage, each pipeline stage in modern processors is designed to process multiple instructions at once. So you can get a CPI ideal of less than 1. And then there are two things when you build these very complex pipelines that you need to start doing in order to not be completely dominated by hazards. The first one is out-of-order execution, which we won't spend a lot of time talking about. It's very important, but it's not something that's going to help you in the design project. The second one is branch prediction, which is a technique to reduce the impact of control hazards, of branches and jumps. And this essentially boils down to predicting better, right? Not predicting PC+4 for the next PC, but doing a better job at predicting where is the program going to go. And as you'll see, this is actually quite important and can give you, some points in the design project with not a lot of effort. So let me just show you, before we get to the techniques, let me just show you one example of a modern processor running one particular program. This is an X86 processor, so I am logged into an X86 machine, and there are multiple programs here. There's this C program over here that's basically just running a long loop to compute some random numbers. It's just basically a lot of ALU instructions and a few memory accesses to a fairly small buffer. This is not really, the point is not to show you, what this particular code is doing, just to show you that there are a lot of ALU instructions here. And now that you know assembly, you can go to any program and any binary and just disassemble it, right? And so you'll see that this is just like the assembly dumps that we give you. Unfortunately, it's X86, it's not RISC-V, but X86 is uglier than RISC-V, but you'll still get what is going on here, right? You have moves, you have add instructions, you have comparisons, you have jumps, jump if equal. So the nomenclature is a little bit different, but the basic subset of operations that you have in X86 processors is approximately the same as the basic subset of, or the basic set of operations in RISC-V. And then you have a bunch of complex instructions that is not worth getting into, right? X86 has over 1,000 instructions, and it's a very complex instruction set. But for the majority of programs, mostly they consist of simple instructions like the ones we have seen. Okay, so pretty much every machine or every Linux machine you use has this handy program called perf. And so let's just run this. What perf does is it shows you performance counters, right? So we've seen that it's useful to have performance counters in processors. Here I'm going to run this ALU instructions program. And this command is basically saying every second, every 1,000 milliseconds, tell me the cycles and the instructions that this program has gone through. So if you run it, it will tell you, every second it will give you a new set of outputs. We'll give you both the cycles for that second and the instructions. And so you can see that each second, this CPU runs through about 3.7 billion cycles, right? That tells you the frequency is 3.7 gigahertz. So the clock cycle time is somewhere, around the 300 picoseconds, 280 perhaps, right? And then every second it finishes over 8 billion instructions, right? So its CPI is less than 1, right? Every cycle this program is computing more, or is finishing more than 1 instruction per cycle. In fact, it's doing around 2.3, right? If you do 8.1 divided by 3.7, that's over 2. Okay, so these techniques actually get you pretty good performance. Let's see them in a little bit more depth. So the first one is deeper pipelines, right? So, the processors that you're going to build in the project, they have 4 stages, 5 stages. It's easy to get 1.5, maybe 2 gigahertz. But if you want to run at 4 or 5 gigahertz like modern processors, you need to break stages. You need to break the processor into more pipeline stages. And so current processors generally have around 15 to 20 stages. In particular, the Intel Skylake and AMD Zen 2 processors, which are basically the latest processors from Intel and AMD, have 19 stages, and they run at between 4 to 5 gigahertz. And that's, 4 gigahertz is a clock period of 250 picoseconds. 5 gigahertz is 200 picoseconds. Historically, these processors, processors are designed so that the amount of logic that fits between two pipeline stages is about the logic that you need to do one addition. And that's because once you start breaking adders across multiple stages, things get very complicated. Now, there are cons to adding more pipeline stages, right? So, you'll have more overlapping of instructions, right? You're running instructions in the pipeline that are separated by more instructions, right? So, you'll have dependencies that span a larger number of stages. And so as we've seen, when going from 5 to 4 stages, we're able to reduce the impact of load to use hazards. The opposite issue happens here, right? If you have, if loads 10 cycles, you'll wait for 10 cycles to get the data that you need if you have an instruction that uses the result of a load. And then, of course, this adds pipeline registers, which adds quite a bit of area after some point. So, in the design project, just some rough numbers. It is possible to get full credit on the whole thing with the 4-stage pipeline, right? So the way the design project is structured, if you haven't seen it, is there are 3 parts. The first part is about optimizing software. The second part is about optimizing hardware, so creating the 4-stage pipeline that I showed before. But it is on, that 4-stage pipeline is running on a very, on a baseline sort benchmark that we give you. So you can't change the software. You're just optimizing the hardware. The third part is about optimizing both, right? So you get your sort program or whatever sort program you want, and you get to optimize the processor however you want. And the nice thing about this is that there's a million ways that you can get full credit. But you can actually get full credit just by being very careful about reducing clock cycle time and having a decent implementation of your sorting algorithm. That said, with the 4-stage pipeline that you'll end up with on part 2, you have basically it's reasonably easy to get to a clock cycle time of 400 picoseconds. If you work hard at it, you can get to 330, maybe 320 picoseconds. It's very hard to go below that. So if you want to really optimize clock cycle time, it tends to be the case. I mean, it's pretty much guaranteed that you'll need to add an extra stage here. And the extra stage is not where you think it is. The extra stage is probably over here, because there's some delay between the instruction cache and decode. And so at some point, it will become necessary to split these 2 stages. And with that, you can get to a clock cycle of about 320, 330 picoseconds without a lot of effort. And if you really want to optimize it, you can get to 250 picoseconds. Okay. So you can do deeper pipelines, wider pipelines, as I mentioned before. The idea is to have a wider, essentially replicated logic in each stage, so that you can process multiple instructions at once, right? And so this lowers CPI ideal. So instead of a CPI ideal of 1 with a width of W, if we can do W instructions per cycle, we can get up to 1 over W throughput, right? Or up to W throughput, so 1 over W CPI. Modern processors use between 4 and 6 wide executions, so they will execute up to 4 to 6 instructions at once. The problem is that if you think about how much effort it takes to do one single instruction per cycle, now if you do multiple instructions per cycle, there are more dependencies that you need to check, there are more cases where you need to stall. Some instructions in the group might go forward while others might need to stall. So this complicates the design, right? So in the handout, one of the very advanced tips that we give you is that there are some ways that you can get a 2-way superscalar processor that would earn full credit, but this is probably the most complicated tip that we give you. Okay, now if you have very deep pipelines and very wide pipelines, we need to also do something else with hazards, because if you have very long latencies for particular instructions, hazards will start dominating execution time. So remember, we have this recipe of techniques to resolve hazards, right? So we said the simplest strategy that we have is stalling. You can always wait for the result to be available, right? So the problem that we have with hazards is you have an instruction that depends, that needs a value that is produced by an earlier instruction. So you can wait for the value to be produced and written to the right place. For example, if it's a register file, you can wait for the data to be available in the register file. You can bypass, you can route the data, right, to the consumer of the data as soon as it is produced. So that's why bypass paths help performance, because they allow us to route, for example, the output of an instruction in the execute stage to the input of an instruction in the decode stage before that result shows up in the register file. And finally, if we don't know the value and we don't have the value yet, we can guess it, right? We can take a guess, and this is what we do with the PC. We guess PC plus 4 and continue executing, and then if the guess is wrong, we need to annul some instructions and restart execution with the correct value. Now, there's another strategy that processors use, which is essentially if you have a stall on an instruction and you don't have the value and you can't speculate and you can't bypass it, you can find something else to do, right? Processors are running multiple sequence of instructions, and beyond that instruction that's currently waiting for its source operands, there might be instructions that can actually run. Now, you'll need to run them out of program order, right? This is why it's called out of order execution. Out of order execution is a really bad marketing name, which is why you will not see this in any commercial processor. They talk about smart execution and dynamic execution. Yes, of course, if you go buy a new processor and they tell you it's out of order, you're not gonna like it. Okay, so to see why out of order execution works, consider this expression, right? We want to compute, this value d, that is 3 times a minus b plus 7 times a times c. So this would be a reasonable sequential implementation of this, where we load A, load B, subtract them to compute A minus B, multiply this by 3, then load C, then multiply multiply with A to find AC, multiply by 7, then add everything up and store the result, right? But, if you actually draw the computation just as a tree or a graph of operations, you can see that you don't need all operations to happen serially, right? So this is what we call a data flow graph. And in a data flow graph, the vertices, or the nodes, are the operations, and the edges between the nodes are the dependencies between the operations. So for example, we could load A and B and C in parallel because they're independent operations. Then we could do the subtract of A and B at the same time or independently from the multiply of A and C over here, right? Because these are different branches of the computation, so they can happen in parallel. Now, you could build a machine that takes in data flow graphs, and there's decades of research into trying to get something like this as the ISA, but there are some complications that we won't go into. What processors actually do is they take a sequential set of instructions, they reconstruct the data flow graph on the fly, so they figure out which operations can happen independently, and then they run them. They run each operation as soon as its operands are available. And this is useful because some operations take a really long time. And so, for example, suppose that you have a miss on this load. So here is a snapshot of execution where this load is waiting, right, is still executing, but we have already completed the load of A, the load of B, the load of B, the load of A, the load of C, and then the multiply, so that we have AC already. We're currently running this second multiply. So we can do each operation, and processors perform each operation as soon as their operands are available. Now, for the kinds of processors that you're building, it is not actually necessary to do this, because you don't have that many pipeline stages. Instead, you can do this in software, right? So for example, if you want to reduce the penalty of this load to use hazard, rather than doing, implementing a processor that does out of order execution, could you reorder the sequence of instructions? How would you rewrite this loop to take fewer cycles? Is there anything you can do here? So you have a stall that comes from this load, producing a result that needs to be used by this add instruction, right? What if we reverse this? These instructions are independent, right? Now you would take one fewer cycle, right? In the 4-stage pipeline, you would actually not stall at all. And so in the design project, when, especially in part 3, where you have control over the software, one very useful trick is to go back to your code from part 1 and rearrange operations so that you reduce the number of cycles. Okay, so the last technique we're going to see is essentially what we call branch prediction. The issue is, once processors do all of these things, remember there are about 20 stages, right, between fetch and write back. And the problem is that we can figure out the outcome of its branch or jump very late in execute. And that's typically around 15 cycles for modern processors. This is what we call a loose loop. And we call it a loose loop because there's a lot of, any sort of loop that takes more than one pipeline stage is going to incur some waste of work, right? So remember, in the 5-stage pipeline, we're losing 2 cycles, right, of work every time we needed to redirect control flow. But here, if instead of 2 pipeline stages, there are 15 pipeline stages worth of difference, and each pipeline stage has 4 instructions, you're wasting many, many more instructions, right? So in general, it's the number of stages, the length of the loop, right, the number of stages between fetch and execute, times the number of instructions or the width of each stage. So in a modern processor, this number is about 60. Every mispredicted branch will cause about 60 instructions to be thrown out, not 2. As you can imagine, if you have one branch every 5 to 20 instructions, let's say about every 10 instructions on average, it's not very efficient if 50% of the branches, you're basically throwing 60 instructions worth of work away, right? Your CPI is going to be horrible. Okay, so, well, this we've already seen. So the trick that modern processors employ to improve performance is to do better predictions, to take better guesses. We've seen how to guess PC plus 4, right? PC plus 4 is a reasonable guess, but it's not a really good guess, right? We can do better. So how much better? I'm just going to show you. I have the baseline sort benchmark code that we give you. This is the standard quicksort that you'll be using in part 2, and I've compiled it for X86. Now, if you run this, this is very short, so this just runs for less than a millisecond. You see that the CPI here is actually not very high. This runs for a little bit over 5,000 cycles, but it only executes 485,000 instructions. Now, luckily, we have additional performance counters that we can check. And so this program has 95,000 branches, out of which 14,000 are mispredicted. This is about a 16% misprediction rate, right? This is actually pretty high, and this is the reason why this CPI is really low. So whereas before, we saw a program that was running over 2 instructions per cycle, here we don't even get to 1. This is about 0.85, a CPI of 0.85. And it's all about this jump and branch penalty, this control flow penalty. Because, again, sort has many branches, at least the sort implementation that we give you, and in general, quicksort has a lot of branches. Now, notice, though, that this processor manages to get about a 15% misprediction rate. So it guesses 85% of the branch targets correctly. Your processor will be wrong about 60% of the time. Right? So 15% versus 60%, you can see that you can get a significant amount of improvement just by guessing better. Now, processors use all sorts of special saws. Fun thing, if you want to see an Intel engineer disappear in a cloud of smoke, just ask them how their branch predictor works. It's amazing. They just vanish. So, that said, even though real processors have just a lot of special saws to try to minimize misprediction rates because it's so important, because your pipeline is very simple, you can do reasonably simple things and still get a lot of performance improvement. So one of the simplest things you can do is what we call static branch prediction. So in general, the probability that a branch is taken is about 60 to 70%. But there are very different cases. And so, for example, this is what we call bias, right? So some branches are biased to be almost never taken. Some branches are biased to be almost always taken. So if you look across branches, you'll see that so branches that go back, right? Branches that jump up in the code to a smaller PC, that is, they're taking about 90% of the time, whereas branches that go forward, that jump to a later point in the code, are taken about 50% of the time. So one thing you could do is take a look at, is this branching back, and then predicting taken, right? Why does this work? Why is it the case that branches that go back are taken 90% of the time? What program structure is likely to be responsible? Exactly, right? This branch goes back, whereas forward branches generally are if statements or some condition that perhaps you have an assertion that's almost never, or a termination check that's almost never taken, right? And so you could predict taken here and predict not taken here. You can also add instructions to bias the branch. Basically, you could have a variant of a branch instruction that says, predict taken for this, right? And the nice thing about this is that you can do these computations in decode. And with the pipeline that you have, with the 4-stage pipeline, you are actually able to eliminate all control stalls as long as your predictions are correct. Your static predictions are correct. So this is actually a pretty easy to do and a reasonably effective technique if you stay with a 4-stage pipeline in part 3 of the project. But we can do better. So what most processors do is they guess the outcome of branches dynamically. And this works because you have locality, because you have temporal correlation and spatial correlation. Essentially, the way that a branch resolves is a good guess for how the same branch will resolve in the future. And spatial correlation, we won't see techniques that exploit spatial correlation, but you can think of a likely path of execution, right? Sometimes you have branches that are related, you have if conditions that are related, so sometimes you can guess that if a branch is taken, then some other nearby branches are also going to be taken or not taken. They're essentially correlated. Basically, the technique that we want here is we have a predictor, we give the current PC to this predictor, and then this makes a prediction. A few cycles later, we'll find out what the actual value for the PC is, and then we'll update this dynamic predictor with the right value so that we'll train it. And over time, this predictor will learn what the behavior of branches is, and hopefully it will make good predictions. Now, there's many different kinds of predictors. We're going to see the simplest possible one, which is called a branch target buffer, or BTB. So a BTB is just a cache for branch targets. Okay, it's a cache that's indexed by PC. So you have a tag, right? This is a direct map organization. There's a tag, is the PC. You have a valid bit, and then you have the predicted target. So the way the BTB works is you index into this cache. This is a small cache. You can make it 4 or 8 entries. You don't need a giant cache. Small BTBs are very effective. And then if you have a hit, you take the target. You take whatever's predicted as a target and use that as your guess for the next PC. If you don't find an entry, then just predict PC plus 4. Right? So what's the idea? That as we have, as the processor runs through the program, it's going to insert the PCs, the target PCs for all the taken branches and jumps into this little table. And then we'll be able to redirect control flow immediately. Here's how it works. So you have the BTB right here at the top of the pipeline. And then you update the PC, you perform a prediction every cycle. This is what we call a tight loop, right? There's no delay in the predictions here. You're immediately predicting the next value. Then, many cycles later, when you figure out that what the right path of execution is, you train the BTB. And if the BTB is wrong, then we can restart execution at the right PC. Okay. Any questions? So, because this is something that's a funny detail, right? For all the caches that we've seen so far, data caches, TLBs, you're actually caching values that the program requires to be correct, right? You can't just say, I don't have the value here, I'll just make something up, right? But a BTB is caching predictions. And so it can be inaccurate and still work correctly, because you always have you have a step a few cycles later where you correct it if it's wrong. So, for example, since it's just a prediction, you can avoid storing all the tags of the PC. Just store a few bits. You can even not store the entire target PC, just store a few bits and use the PC, concatenate the other bits of the PC with the bits of the target that you have. If you have a long jump, then whatever, you'll always be incorrect for that jump, but in general, jumps and branches have short targets. And you even could omit the valid bits, right? And so if you find anything, you can just predict that it is taken. Okay, so this translates to a module with a fairly simple interface with a predict method, and then in the fetch stage you get the next PC from the given PC, and then on execute we train the predictor by updating it, right? There's an update input that takes the PC, the actual next PC, and whether the branch was taken. So this is a pretty easy way of getting some points on part 3 of the project. You can do static branch prediction if you do a BTB. So a BTB is going to be pretty much necessary if you're looking for a log clock cycle time, or if you have more than 4 stages. So if you go to a 5 or 6 stage pipeline, a BTB is going to be much more effective. Okay, just there's a couple of slides here on essentially doing better predictions by using 2 bits instead of 1 bit. Modern processors are actually using many different kinds of predictors. They don't only have a BTB, they have more accurate predictors further down the pipeline. And so there are predictors, for example, for loops, for call and return sequences, for branches, and so on. Okay. And so just to put it all together, let's take a look at the architecture of a representative modern design. This is a little bit old. It's from 2008. It's the Halem Core i7, so this was introduced by Intel in 2008. The reason I'm showing it here is because it was fabricated on the same technology, 45 nanometers, which is about the same technology that you will be using for the design project. So this had north of 500 million transistors, 256 square millimeters, and if you dive in, you can actually see the structures, in this chip. So there's 4 different cores, all sharing an L3 cache. They have L1 and L2 caches that are kept coherent with the coherence protocols we saw in the previous lecture. And if you look into the structure of its core, you can actually see the different components. So you have the L1 data cache here, the L1 instruction cache here, and there's sort of the whole pipeline goes this way, right? So there's fetch, branch prediction, decode, scheduling. You actually get the execution units over here, the data cache, and so on. And the L2 cache is over here. Now, there's one thing I want to conclude with is that if you look at the overall area of the core versus just the amount of area that's devoted to the execution units, it's actually kind of amazing that about 1/6 of the area is devoted to actually doing things, and 5/6 are devoted to just doing them fast, right? It's all caches, it's all prediction structures, and so on. But it's even worse because if you actually compare the area of this versus the area of your RISC-V core, this is your RISC-V core, the RISC-V core in the lab in comparison. So it's about, between 100 and 200 times, from 100 to 200 times larger than a very simple core. Curiously, it's about 10 times faster. So it's not the greatest efficiency. However, if you want fast, this is essentially the way to get it. Okay, so with that, this concludes the last lecture of the course. So we hope that you've enjoyed the material as much as we've enjoyed teaching it. This is not the end of the course though, because for the next, so of course we have the quiz on Thursday. Good luck on the quiz. But also over the next week we'll be in lab and also on Piazza helping you with the design project. All right, thank you.